Hi, in this video, we want to take a look at the partial autocorrelation function for autoregressive moving average models. All right, so we're interested in looking at the autocorrelation of a time series that we're modeling as autoregressive moving average, and we want to eliminate like middle correlations when we look at the autocorrelation. Okay, so why do we want to do this? Well, because this is a good way for us to determine the degree of our model for autoregressive model or a moving average model. All right, so here, take a look at this table. If you get nothing else from this video, check out the table that's underneath the orange right here, the behavior of the autocorrelation function and partial autocorrelation functions of autoregressive moving average processes. Okay, so in the first row, we have the autocorrelation function. And when we talk about autoregressive moving, there's autoregressive models, the autocorrelation is going to tail off. But if I had a moving average model, the autocorrelation would cut out after lag Q, okay? And if I have an ARMA model, the autocorrelation function is going to tail off. All right, well, now let's think about the partial autocorrelation function. If I have an autoregressive model, the partial autocorrelation is going to cut off after lag P, okay? And if I had a moving average model, the partial autocorrelation is going to tail off. And for an ARMA model, the partial autocorrelation is going to tail off also. All right, so how do we use this in real life when I'm looking at real data? Well, what I'm going to do, I'm going to look for the autocorrelation or the partial autocorrelation to cut off. If I see that the autocorrelation cuts off after some lag value and the partial autocorrelation tails off, that tells me I want to use a moving average model. And I'll use the point where it cuts off to select the degree of my model. Now, if I see that the autocorrelation tails off and the partial autocorrelation cuts out after a certain point, then I'm going to go with an autoregressive model. And I'm going to use the partial autocorrelation to determine what degree I should use. Now, let's say that I believe I should use an autoregressive moving average model, and neither one cuts off, they both tail off. If the autocorrelation tails off and the partial autocorrelation tails off, then I'm going to want to use an ARMA model. Okay, so this is looking good. Let's go ahead and give credit where credit is due. I'm taking examples in code from time series analysis and its applications. Here are the authors of the textbook. Here is our GitHub page, and students can download this textbook for free through UCF's library. All right, so now let's get to the actual content that we want to talk about. So if you get nothing else from this video, that table alone is worth your time to take a look at. That is the single most important aspect of this entire video. That's why I put it first. All right, so let's think about a partial autocorrelation function. And for this, to get us going, let's think about a moving average model of degree Q. Well, it's going to have zero autocorrelation for lags greater than Q. And then at exactly Q, we know that the autocorrelation will have to be non-zero. We can use this fact to identify the order of a moving average process. Okay, and so I'm basically talking about the table we just looked at for the moving average column. However, if the process is autoregressive or it's an ARMA model or an ARMA process, then the autocorrelation function tells us very little because it's just going to tail off. Now, if I have a moving average process, I'm going to use autocorrelation to determine the degree if I have an autoregressive model, an autoregressive process, I'm going to use partial autocorrelation to determine the degree. And if I see that ACF and PACF tail off, then I'm going to use an ARMA model. Okay. All right, so now let's start talking about partial autocorrelation. Partial autocorrelation is going to be the correlation of our variables that we're interested in after we subtract off the regression of another variable. So this x hat, so I've got three variables. I'm interested in the partial correlation between x and y in this situation. But we have this third variable. I want to eliminate any linear relationship there is on this third variable. I want to eliminate any aspect that could be going on with this z. So what I'm going to do, I'm going to regress x onto z. Then I'm going to subtract that regression part off. I'm going to regress y onto z, and then subtract off the resulting regression. Okay, so the partial correlation measures a correlation between x and y with the effect of z removed or partialed out. All right, so now it's going to work out that if x, y, and z are multivariate normal, then this measurement is going to end up being the correlation between x and y conditioned on z. So if I'm using multivariate normal, this will be like directly what I would get after if I was to go take multivariate normal, condition on the value of z, look at the resulting multivariate normal that I would have, and took the correlation, I'm going to get the exact same value. All right, let's run through an example using an AR1 model. So let's say that I have x of t is equal to some constant times the previous observation plus some white noise. All right, so let's go ahead and check out the covariance between the current observation and 2 back. Well, if I think about it for a moment, x of t depends on x of t minus 1, and x of t minus 1 depends on x of t minus 2. All right, so because of that chain of relationship, that chain of dependence, I know that x of t depends on x of t minus 2, 2 steps back. All right, so I know it can't be 0 just intuitively. And what do I actually get off of this if I'm doing an AR1 model? I can see that we're going to, the actual autocorrelation for 2 steps back is going to be phi squared, and this is going to connect directly to the variance of the white noise. Okay, so if I sat down and I wanted to work this out, then x of t plus h is going to be that coefficient to the power of h times x of t, and then I'm going to have that coefficient to lower degrees times the white noise. All right, so if I want to use this, if I want to figure out what is the autocorrelation, I can sit down, I can work this out. Now, the important thing here is to notice that this will never be equal to 0. This connects to the variance of the white noise, and this is a non-zero value. Therefore, even for large values of h, it's going to be non-zero. All right, so this kind of gives us like an intuition, this should help convince you that what I said about the tailing off aspect is correct. And remember that if I'm talking about x of t plus h, it's dependent on the previous one, and that previous one is dependent on 2 back, and that 2 back is dependent on 3 back, and so on, all the way back to the earliest observation we're interested in. And so because of that chain effect, we know that x of t plus h will be dependent on x of t, for any positive H. All right, so let's go ahead and go back to that AR1 example we were just talking about, and let's go ahead and remove that middle part. So we've got x sub t, we have x sub t minus 1. Now what I want to do, I want to do that regression aspect I talked about a moment ago, and I want to subtract off the projection onto t minus 1. All right, so what I want to do, I want to take x sub t, I want to subtract off x sub t minus 1. I want to, after regression, and then I want to regress x sub t minus 2 onto x sub t minus 1, subtract the regression part off, and let's see what happens to our covariance. Well, when I do this, if you sit down and crunch this out, we're going to end up getting white noise terms of different indices. And since there are different indices, we know the correlation or the covariance is equal to 0. All right. Okay, so let's look at the partial autocorrelation for mean zero stationary time series. Let's go ahead and say that wide hat x sub t plus h is the regressed value I get from taking x sub t plus h and regressing it onto the previous observations. Okay, well, when I do that, I'm doing regression. I'm going to have coefficients times the other variables, and I'm going to get this as y hat x sub t plus h. That's my modeled value using that regression projection. Now, no intercept is needed because we're doing a mean zero time series. If I did not have mean zero, what I would do, I would replace x sub t with x sub t minus the global mean. All right? Now, something that's important for this is that for this time series, for this process, and for this argument to make sense, we have to have a constant mean going on for all time values. All right, so what I can do, I could go through and I could shift this index, and by doing that, I get a projected value for x sub t, and I get exactly the same coefficients if I do the regression because of the stationary aspect of the time series. Okay. So now let's take a look at the partial autocorrelation function. For partial autocorrelation, if it's just one step back, it's just going to be the correlation between two consecutive values. If I'm going to have h separation between there, what we're going to do is I'm going to take x sub t plus h. I'm going to subtract off the regressed value of x sub t plus h onto the previous values between here. So this wide hat comes from regressing this value onto these previous ones. Okay. And then we take x sub t and we subtract off the regressed value. All right, and so now we'll compute the autocorrelation function after doing the subtraction. Now, if x sub t is Gaussian, then it's going to work out that this partial autocorrelation is going to give us the correlation coefficients of the bivariate distribution after we condition on those in the middle values. All right, so let's compute the partial autocorrelation function of an autoregressive model, an autoregressive degree 1. So we have x sub t is equal to a constant times the previous observation plus some white noise. And we're going to go ahead and say that our coefficient is less than 1 in magnitude. All right, well, intuitively, it should be very natural that since the white noise has a mean of 0, the regressed value onto the previous observation, the coefficient is just going to be the coefficient from the model. That should be intuitively obvious. Now, let's say you don't believe me. Let's say like, no, I don't accept this. I want you to actually crunch through this. All right, let's go ahead and do that. So how do I show that this partial autocorrelation is equal to the coefficient I have up here? Well, what we're going to do, I'm going to say that white hat is equal to a constant times the previous observation. Okay. Now, notice I don't have an intercept. I don't have an intercept because I have expected value of 0 across the board. All right. So now I'm going to take the expected value of x of t plus 2 minus the regressed value. So what I need to do, I need to pick the regression model that will minimize this because we're doing a projection, which is the same as regression. All right, well, here is my model, which is just one step back. And so I'll go ahead and put that in. Now what I'm going to do is I notice that this is being squared. So I'll go ahead and square it. It's hip to be square. Boom, I've got this. Now what I'm going to do, I'm going to go through and take that expected value. Now remember that x of t has constant variance and we have 0 expected value. That means that when I take the expected value here, that's equivalent to the variance. When I take the expected value here, that's equivalent to the variance, or gamma of 0. Now here, when I take the expected value, that's going to be the autocorrelation of a shift of 1. And so then I get all of this working out. And I realize that that is a quadratic on the beta coefficient. That's a degree 2 polynomial on the beta coefficient. All right, and we have positive coefficients, in fact, because variance has to be positive. Therefore, to minimize, I want to take the vertex of the degree 2 polynomial, so negative b over 2a, and which gives me this. We know that this is equal to that. And so, boom, we get what I claimed previously. All right, so now what I'm going to do, I'm just go through and do the computation here. And we're going to end up getting white noise and white noise inside a correlation, which is going to be 0. Easy peasy, lemon squeezy. So in fact, for this type of model, for any h, we're going to have a partial autocorrelation of 0 for this particular one. Now let's consider the partial autocorrelation for an autoregressive model of degree p. Okay, so let's go ahead and say that we have an autoregressive process of degree p, and we're going to go ahead and say that our roots are outside of the unit circle for the corresponding polynomial. All right, so here, when I say autoregressive of order p, I know that I've got p shifts back, coefficients times the shifted values back, plus some white noise. Okay, so now when h is greater than p, the regression of t plus h value onto the middle ones is going to end up just being this. All right, that should be kind of intuitive. Notice that matches up with here. So for larger values of h, I'm just going to take exactly what I have here, and I'm going to drop the white noise aspect for my projection. Now, when h is, okay, so this should be h is less than p. All right. When h is greater than p, there's going to be 0 partial autocorrelation between the observations. So when h is greater than p, then we're going to end up getting, once again, white noise in a correlation with a difference index. Therefore, the correlation is going to be equal to 0. This has a mistake. I will fix that. And realize that when I look at this part, x of t minus its projected value depend on white noise of lower indices. All right, so when H is less than or equal to P, we know that the partial autocorrelation will not be equal to 0, and the lower indices, partial autocorrelation may or may not be 0. All right, so let's go ahead and demonstrate this for an AR2 process. So here are my coefficients for my AR2 process. What we're going to do, we're going to use the ARMA ACF function. This is in base R. Here's my coefficients. I'm going to say that we have 0 for our moving average, and I want to have a maximum lag of 24. Here we have an autoregressive moving average, autocorrelation function once again, same coefficients, but this time we're going to compute the partial autocorrelation function. And let's go ahead and take a look at the time series plots. And so here, AR2, we see that the autocorrelation is going like that. And we can see, boom, it disappears when we look at the partial autocorrelation. Now let's consider the partial autocorrelation function of an invertible moving average process. So it's an invertible moving average process, means that in fact I can write x sub t in terms of all these other ones. So realize that what I'm doing is I'm taking the invertible process, and that means that I can represent the white noise in terms of an infinite sum of the observed time series, and I'm using that fact with the moving average to replace all those terms in here. Now, something about this, there's going to be no finite representation in terms of like an auto-regressive aspect off of this. And because of this fact, the partial autocorrelation is never going to cut out for a moving average process. So let's take a look at this. So if I sit down and do the computations with a moving average 1 process, so here is current white noise, here is the previous white noise. We're going to say that our coefficient is less than 1 magnitude. Then here is my partial autocorrelation for a given value of h. And you'll notice that that will never be equal to 0. All right, so now let's actually use this as an example. Let's go ahead and take a time series, and let's take a look and see what should we do. All right, so let's go ahead and use the recruitment time series from the AS-TSA package. All right, so let's go ahead and plot the autocorrelation function and the partial autocorrelation. So I see that I have partial autocorrelation cuts out after 2, but the autocorrelation tails off. Okay, so that tells me immediately I'm interested in an autoregressive model of degree 2. If both of these tailed off, then I would look at an ARMA model. I wouldn't know the degrees at this point, but I would have a direction to go. If I saw the autocorrelation cut off and the partial autocorrelation tail off, then I would be going with a moving average model, but we're going to use autoregressive. All right, so now what we're going to do, I'm going to use the autoregressive ordinary least squares function in base R. Here is my time series I'm fitting. Here I'm saying I want order 2. We don't need to remove the mean. And here we're saying to have an intercept on there. And so here are my coefficients. And we can look at the standard error of my coefficients. Now, there are other ways to fit this. There are other methods. Here are some major ones that are listed in R. And so here I just went through and just fitted a bunch of them just to fit them. I just kind of played around with it. Now, you'll notice that if I put an order max of 12, Yule Walker had the good sense of giving me only 2 because it saw that it cut out. The algorithm did the smart thing and said, hey, I'm going to stop at 2. And you notice, once again, Berg stops at 2. Ordinary least squares, maximum likelihood. All of these only gave me degree 2 because of what they saw in those plots. And so we can manually call each of these functions directly ourselves. And here I'm just plotting the time series, and I'm plotting the predicted values. So the black are the observed values, and the red are the predicted values. And how this model ended up is that it flattened out after it hit this point. All right, well, that's all I've got for you. Life is short, do math.